Welcome to this eLearn Security video training lesson on WPA handshake capture and brute force. In this video we will explore various techniques useful to crack WPA and WPA2 network keys. As you know from the theory study, WPA and WPA2 do not suffer the flaws that plagued web encryption. Because of that, the best option we have against these security mechanisms is a brute force attack. Brute forcing a WPA key is an offline attack, meaning we can perform all the necessary computations on our PC completely off-site. The only active part consists of gathering the four-way handshake between the network access point and one of its clients. In the first part of the video, we will show you how to get this handshake, and we will analyze one capture using Wireshark. In the subsequent part, we will concentrate on various tools you can use that will help in finding the passphrase. In our test environment, we've already set everything up. Let's start AeroDump-ng and see what we get. Of course, we assume you already have set your interface into monitor mode in order to proceed with the next parts of the video. We'll use the command AeroDump-ng --BSSID filter to focus the capture only on our test network. This will minimize the number of collected frames and will ease our analysis. As you can see from the output, we got our lab network access point. It is configured to use WPA plus TKIP security. We've been lucky, in fact. Examining the stations list, we can find an already associated client that is exchanging traffic with the access point. This is a major requirement for WPA cracking, at least in its first phase. If we weren't lucky to find an associated client, we wouldn't be able to obtain the four-way handshake to perform the attack. Take note of the network BSSID and of the MAC address of the client using your favorite text editor. You will need this data shortly, as we're going to launch a deauthentication attack against the client using AirReplayNG tool from the AirCrackNG suite. Let's now open a new terminal window, leaving AeroDump-ng working in the background. You can place the two windows one next to the other. This way you'll be able to spot the exact moment when AeroDump gets the handshake. Use AirReplayNG to deauthenticate the client. To do this, use the following command, and after the -A, copy the MAC address of the AP, then use the -C and place the MAC address of the victim client. Mon0 is our interface as usual. After a few seconds, you should receive a notification from AeroDump-ng informing you that a WPA handshake has been captured. In fact, in our previous window, we can see this message. So after that, we can stop the injection process if it is not yet finished. Close AeroDump-ng and prepare for the next attack phase. Okay, let's see what we've got. Let's fire up Wireshark and open the fresh capture file. Depending on the network traffic, you could get a lot of frames. Obviously, this is all encrypted. For example, let's open one data frame. In this one, you can see that the data portion is full of nonsense characters. In the frame header, we can also see the TKIP algorithm initialization parameters. Similarly to web, TKIP has an initialization vector 2, but as you can notice, it's only 8 bytes long, not just the 3 as we saw in the weaker security scheme. All of these frames are of little interest to us. Right now, we would like to focus only on 4 of them, namely the handshake. To ensure that we can focus on those 4 frames, you can apply a simple Wireshark filter expression. We can write EA-POL in the input field and press enter. We got exactly 4 frames. In fact, during our capture, only one handshake took place. This may vary depending on the environment and the number of clients associated to your test network. Also, some frames could be transmitted multiple times due to errors and timeouts in the communications. So you could receive more than one instance of the same handshake frame. Also, due to the nature of the deauthentication attack, you could find truncated handshake sequences that were interrupted by the deauthentication frame's flood. Now let's examine the first two frames of the handshake. If we look at the frame control field, we can see that the From DS flag is set. This means that the frame was sent from the authenticator, namely the AP, as we know from the theory study. Let us close this branch and examine the payload. Here we can see the A nonce, one of the components used to generate the PTK on both sides. It is a 32-byte string. In the first frame, the MIC, the message integrity code, is all zeros, meaning no MIC was really calculated in this first phase. In fact, this would not be possible because the PTK used to encrypt it has not been built yet. Let us check the second frame. This time, the 2DS flag is set as the message goes from the supplicant to the authenticator. The client sends its S nonce, but this time, given that it's built to PTK, it also generated the proper MIC to send along. After this handshake overview, we can close Wireshark as we're going to dive into the real action. What you need for a brute force attack against a four-way handshake is a dictionary file. You probably already have built one word list, but if you did not have one handy to pass on to our brute forcing tools, you can always download a pre-built one. Just query your favorite search engine and look for a WPA optimized word lists. These will only contain words with links between 8 and 63 characters, a requirement for WPA passphrases. For our demonstration, we use the very famous RockU word list. It contains more than 1.4 million words for about 130 megabytes of data. However, this list is not WPA optimized, and as such it contains words that will never match a WPA passphrase such as 1, 2, 3, 4, 5, 6. This will be a good occasion to demonstrate how you can simply optimize an existing word list for WPA and WPA2 penetration testing. For this task, we are going to use good old password inspector tool already available in Kali Linux. From inside the directory that holds the word list file, launch the following command: pw-inspector-i rocku.list-o optimize.list-m 8-M 63. When you run this command, it will filter the word list and output only those passwords matching the given length restrictions. If we check the number of lines of both files, we can see PW-Inspector reduce the final number of words of about 500,000. Now that we have an optimized word list, we can use it against a four-way handshake. Our first brute forcing attempt will use the famous AirCrackNG tool we already encountered when we were doing the web cracking, only this time we will try its dictionary attack mode. From the previous terminal window, write the command aircrackng -w optimize.txt and use the path of the .cap file containing the captured handshake. Okay, let's run it. And here it is. Aircrack found our passphrase in a couple of seconds. As you can see, here is the passphrase. Above the output, we can see some details about the cracking process, like numbers of tested keys and the cracking speed. It took only 1,300 keys to find our password, but we were lucky. In fact, at the reported speed, testing all of the 1 million word list files could have taken about 15 minutes. This is not a great achievement, especially if you consider that we used a very small word list file compared to the ones which are typically used for this kind of attack. How can we improve these numbers? We could use a multi-core system, but even that will not give us a significant improvement. What we really need to do to boost our attack performances is use the power of a modern GPU. Over the last few generations, GPU manufacturers have evolved their architectures to not only perform graphic processing, but to also provide the computational power for highly parallel processing tasks. We're now going to exploit this power for cracking passwords. There are several tools available for most platforms, specifically designed for this kind of task. For our demonstration, we're going to use the Windows version of OCL Hashcash. You can find the download link there too. To be able to use the captured handshake in OCL Hashcat, we need to convert it to a specific format called Hashcat Capture File. The fastest way to make this conversion is using aircrackng -J option. From the old terminal window, we'll type this command, aircrackng -J hashcat, and specify the original capture file. Here we are. The capture file is stripped down and reformatted in a way that is understandable by OCL Hashcat. Now we can take the Hashcat file to the Windows-based PC and feed it into the brute forcing software. Let's move to a Windows machine for the next phase of this video. Here we switch to a Windows machine. We already have downloaded OCL Hashcat and extracted it in our working directory. We also copied over our word list file as we will need it as well. OCL Hashcat provides different binaries to use. We have alternative versions for CUDA and OpenCL GPUs called CUDA Hashcat and OCL Hashcat respectively. Each of them comes with a 32 and 64-bit version, so you will need to choose the best that fits your machine and its architecture. Remember to update your GPU drivers to get the best performance with this tool. Also, you will need to use drivers from NVIDIA or AMD, as Windows basic drivers will be useless for this type of function. From OCL Hashcat folder, we'll run this command. Before running the command, let's examine the options. At first, we're going to use the CUDA Hashcat as we are running on an NVIDIA machine. Then, the obscure 2500 number is the only OCL Hashcat numeric notation for WPA and WPA2 handshake attacks. And as the last portion of the command, we type the word list file. Now let's run it. Hashcat starts crunching. As you can see from its output, we got a performance increase factor of 5, achieving almost 4,000 keys per second. Even if these numbers seem good to us compared to the plain Aircrack NG, we've only scratched the surface of what we can achieve with a decent GPU. High-end cards actually can crunch over 100,000 keys per second, while low-end mobile GPUs, as the one we are using, are not really suitable for the task, so investing in a new GPU is a good plan if you're going to do a lot of wireless network assessment. Let us now go back to our Kali Linux machine for the last part of this video. We would like to examine one further option you have as a penetration tester when it comes to cracking WPA and WPA2 handshakes. In fact, you don't always have the computational resources needed for a heavy brute force attack. While investigating in a dedicated hardware environment is certainly advised, you can still make use of cloud services for better performance. There are a number of websites nowadays that offer online cracking services based on a highly scalable hardware architecture, usually for a small fee. One of the first to be published is Cloudcracker, reachable at www.cloudcracker.com. From the home page, you just need to select your capture file, type the SSID name, and then click Next. You will be given the possibility to choose the attack dictionary size. The bigger the final dictionary used, the higher the price you will need to pay. What is really amazing of these tools is the expected maximum attack time. Even with the largest dictionary, it will take 2 hours maximum to finish. Compare this number with our performances earlier, and you'll see that it can be worth a try. The next step requires us to input the email address to which the final results will be sent. Finally, we will need to provide credit card information. As of now, we can even pay using Bitcoins. We have come to the end of this video. We hope you enjoyed learning how to crack WPA and WPA2 network keys. Following the instructions, you are now able to capture a 4-way handshake and select your best option to determine the passphrase from it. Thank you for joining us.